What's up, Beast? Welcome back to the video. Let's learn some math. Alrighty, Beast. Number 38. Describe the transformations of each function compared to its parent function. So we're given the parent function f of x is equal to 3/4 square root of x plus 1. So the parent function here. So the parent function, like, imagine you got rid of just like all of the random stuff that doesn't actually matter. So like in here, just like random numbers. So like you could get rid of that. You know, these are all just transformations. They don't actually really affect the curve. So like the square root of x function, can't remember exactly what it looks like. I think it looks something like kind of like that. So like if you have like this equation, for example, sorry, let me see if I how to move stuff. So like this line right here, so like say it's like 3, so say it's like plus 1. So this would be like the standard line, right? If it's plus 1, it's gonna like move up. So it's not actually affecting the line itself. But now, for example, if we had like 3/4, it just like stretches it out, or I guess 3/4 like shrinks it. So you know, so those don't affect how the line itself actually works, whether it's like down or, you know, if it's like a linear curve or something like that. Like those are all types of lines, and 3/4 and plus 1 don't actually affect what kind of line it is. The square root does. So let me clear this off. They changed my notes app. Very upsetting. Okay. Let's change it to green. So we know that the parent function is going to be y is equal to the square root of x, because really 3/4 and 1 don't matter for determining what kind of line it is. So now it wants us to describe the transformations, right, compared to the parent function. So what's happening here in this function versus what's happening in this function. So in this function, we have a 3/4 vertical shrink, because it's directly affected by the x value. And then we have a vertical reflection over the x-axis. Or wait, no, we don't. That's a lie. Never mind. Ignore I said that. And then we have a vertical shift up 1. And that's because we have this this plus 1 value that's going to move it up. And then the shrink. So it's only the difference between a shrink and a stretch is what kind of fraction it is. So if we had like 1/1, this would be the parent function, right? This is what it is. So if we had 5/4, you can think of the square root of x as getting bigger, whereas we had like 3/4 of x, right? It's getting smaller. So this would be a stretch, and this would be a shrink. Okay. So now we're going to move on to 39. So here you can kind of see what's happening here. We can determine that, remember what I said, this kind of stuff, that one does matter. This doesn't really matter. This plus 5 doesn't really matter. This -8 doesn't really matter. So our parent function is really just the cube root of x. Everything else is just little modifications to what the original curve looks like. So in this one, we can see that there is a inside the what's it called, the not radical, maybe it's radical, yeah, inside, no, the root sign, you know, inside this shit, whatever it's called, that's where your horizontal transformations occur, right? So horizontal is under the root sign, and vertical are outside the root signs. So in this case here, right, we have a horizontal shift left 5. And now it's left because when it comes to horizontal shifts, it's the opposite of whatever the sign is. So think of it like if you saw, like, in parentheses, you have like x minus 5, right? That would be x is equal to a positive 5. It works the same concept, right? Yeah. Erase that. All right, and then the second transformation we have is a vertical stretch by 2, right? We can see that in the front. See that vertical stretch by 2. And then there's that third one that is the vertical shift down 8. Bang! Let's move on. Number 40, asking the cubant parent function is reflected about the x-axis, then shifted so that its point of inflection is located at -6, -2. Write an equation that represents this new function. So for 40, let's see. Okay, so let's see if we know. Let's just be very basic, right? So we have, it's cubic, right? Cubic means to the third. So we have y is equal to x to the third, right? Is reflected about the x-axis. So what does that mean? We can now move to saying it's reflected across the x-axis, which means it's negative, right? And then to move it to the point of inflection at -6, -2, we're going to have to move it left 6 and down 2. And remember, for horizontal movement, that happens within the x, so we're going to have y is equal to -x plus 6, remember it's the opposite, cubed. And then for that down 2, we just tag that on at the end. So up and down happens right at the end, and left and right happen to x. So moving on to 41, let's graph this out. So let's start off just by writing the parent function, right? Remember this this negative doesn't matter, this 6 doesn't really matter, this 5 doesn't really matter. For the parent function, it doesn't matter for graphing it out. So we know the parent function is really just that. So let me uncover this. So whenever you're graphing stuff, just do like 5 points. That's the easiest thing to do. So for here, when we throw in 0, what do we get? 0 is always a really easy one to figure out, usually. Well, actually, in this case, 0 is not an easy one to figure out. Let me move the parent function. We don't really need that right now. So for this one, let's see -5. So when x is equal to -5, because that's an easy one, right? Because we know what the square root of 1 is going to be, which is just 1. So we then have y would be equal to -1 plus 5, which is equal to 4. So now we have 1 point, -5, comma 4. So we go 1, 2, 3, 4, 5. 1, 2, 3, 4. So we have 1 point there. And then what's another easy thing that we can get the square root of, right? 4 is another good one. So we could do x is equal to, what would give us 4? -2. So when we plug in -2, what y value do we get? We'd get -2 plus 5, which would be equal to 3. So we go -2, 3, 1, 2, 1, 2, 3, right? Now we can look for another, let's see what else is easy. Yeah, so let's go from -6. Let me see. So 3 would be another easy one, right? So we can do x is equal to 3 because we know what the square root of 9 is, right? So x is equal to 3, square root of 9 is equal to 3. So -3 plus 5 is equal to 2. So we go 1, 2, 3, 1, 2. And then what's another easy one that would come after that? 16 is probably the next closest one. So let's do x is equal to 10. So negative 4 plus 5 is equal to 1. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1. So you can kind of see how this curve is starting to work out. And for the sake of it, just to see the full ease of it, we're going to actually do one more. Let me move this out of the way here. Let's do, what would be another good one? That would actually be the end of what we could do. So here's where the domain is going to start coming in, right? So we know that for root functions, right, you cannot have a negative number inside in the root, right? So what this is saying right here is that the x value can never be lower than negative 6. Because if it was negative 7, it would be negative 1, and we'd have imaginary numbers, and then things would get really crazy. So the lowest number that we could have in here, because the square root of 0 is 0, right? So if we plugged in anything lower than a negative 6, we would have problems. So that's where our domain comes in, right? Because that's an x value. So we know that you could plug in negative 6, but you can't plug in anything lower, so you're going to have that bracket here, right? The bracket means that it is that number specifically that could go in. So if you had actually don't overthink anything else. Just if that number, so negative 6 can work in this function, then it's okay. And actually we'll throw that in. So x is equal to negative 6, and that gives us 0 plus 5, so y is equal to 5. So at negative 6, we have, let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, right? And we're actually going to have the line basically go like that. And the value can't go any further than this. You can almost imagine there's an imaginary line here. Don't actually draw the line, but you can imagine there's a line there that stops it from being able to go any lower. And you can see that this line, because once it keeps going in the positive direction, really can go to infinity. You can plug any positive x value in for the domain, right? If we plugged in 100,000 plus 6, you can get the square root of 100,000 plus 6. So that value does exist. Now for the range of y values, right? Let's see. So this is going to work the exact same way, right? Because we know that this point right here is the last possible point. This is kind of annoying. So that point is the last possible point. But like I said, if you zoom out, you'll see that this line kind of goes all the way down for infinity, right? You can see it goes down. It'll keep going down forever. So our range is going to be from negative infinity, right? Because it's coming up, all the way up to 5, which is where this point is, the last possible point that we could have. So that also tells us where our endpoint is, right? Our endpoint for this line is going to be at negative 6, 5. So now the end behavior is basically just asking the same thing as the domain expansion, or not domain expansion, as the domain and the range. So as the x value, right? Let's see, wait, is x... Okay, yeah, so this is asking about the end behavior. So as x goes to negative 6, right? Because that's where we start having problems at. Y goes to 5. And as x goes to infinity, y is going to go to a negative infinity, right? As the x value increases, the y value decreases. We'll leave it, it's fine. All right, the increasing interval. So we can look at this graph and we can just see that it's never increasing. It's only ever decreasing. So we can just say none. And we can say that this graph is decreasing from the endpoint of -6 to infinity. Boom. Now for this next one, it's very, very similar, right? So we can say, we have the horizontal stretch of 4 and it's shifted down 7, right? So we can start graphing some points. So if we plugged in 0, all right, so we'll say x equals 0, y is going to equal -7. So we can go down 0, 1, 2, 3, 4, 5, 6, 7, right? Now we can do x is equal to 1, and y is going to, so we have the square root of 1, which is 1, multiplied times 4 is 4 minus 7, we have -3. So we have 1, 1, 2, 3. Now we can plug in another easy one, would be 4, right? Because we know what the square root of 4 is. So we have square root of 4 would be 2. 2 times 4 is 8. 8 minus 7 is 1. So we have 4. 1, 2, 3, 4, positive 1. And we'll do one more point for the love of the game. And x is going to be equal to 9. And square root of 9 is 3 times 4 is 12. 12 minus 7 is 5. So we have 9 comma 5. 5. And this line will keep going forever, right? So this brings us back to the part where you cannot have a negative number in a root function. This only applies to the square root as well. So if you have a cube root like that, you can have negative numbers. That does work. This only applies when you have the square root. So in this case here, we have our curve drawn. So we know that our domain, right, our x values, they start at 0 because if we plugged in -1 to the function, right, that doesn't exist. You'd have a -1, you'd have imaginary numbers, yuck, yuck, yuck. You don't want any of that. So we can almost kind of just draw that imaginary line here. And you know what? Here's what they will tell you to do. I don't know if you guys did this in class, but they want you to do dashed lines. So draw a dashed line, right? I would replace the other ones, but I'm too lazy. But do dashed lines. So now, I'm sorry, let me change it back to solids. Our domain of x, and remember, domain is our x values. Our x values, our possible x values, are from 0 to infinity, right? Because the x values can keep going forever. You could put positive 1 million in there, and you could get the square root of positive 1 million. And then for the range, which is our y values, we know that same thing here. We'll draw the dashed line. Our y values can only go from -7 to infinity. Now our endpoint, because we can see where the endpoint is, where things start having problems, is 0, -7. So now, as x goes to, let me see what it wants us. This is 42. Yeah. As x goes to infinity, right? As x goes to infinity, what happens to y? Y also goes to infinity. Now, as x goes to 0 from the positive direction, y is going to go to -7. So we know that the increasing interval is always, right, because this line is never decreasing. So for increasing, we're increasing from the x values of 0 to infinity and decreasing never. So now we're gonna move on to up here, 43. So now this is an example where you can have negative numbers under the graph here. So let's see, we have a cubic function or a cube root function that's going to be shifted to the right one, right? Because remember that horizontal shift happens under the root and it's opposite to what you'd think it would be. So it would be to the right. So we can start graphing some numbers here. And these are a lot easier to graph because there's a lot more options. So we can just do x is equal to 0. And y is just going to equal -1, right? X is going to equal 1. Y is equal to 0. Let's see, we can shake it up. We can do x is equal to -3. Y is going to be equal to a -2. X is equal to, let's see, let's throw in another positive number here. Let's see, 4. Yeah, 4. Or not 4. Let's do 5. And then y is going to equal, let's see, that would be, oh shoot, wait. My bad, hold up. I made a little fumble here. Ignore these values. TS did not happen. This one's okay, actually. Forgot cube. My bad. Cube is doubled, right? Yeah. So now we're looking for common cubes. So let's review this real quick. Common square root ones, right? If we're given square root stuff, common ones, we know the square root of 0, we know the square root of 1, we know the square root of 4, we know the square root of 9, 16, 25, ... Come on, you got the rest of them. Now for cubic, our easy ones are 0, 1. The next one we're going to have is 8. Because remember, 2 times 2 times 2 is 8. Now 3 times 3 times 3 would be 27. And, I mean, you could go higher than that. Next one is 64. ... So, for this one, remember, we just do easy values, and this only goes up and across by 10. So, we got to make sure whatever we plug in is able to do that. So, let's do x is equal to 1, which is going to be equal to, y is going to give us 0. Now, we could try to get to 8, right? So we could do x is equal to 9, and y is going to give us 2, because remember the cube root of 8 is 2. And let's go in the negative direction. So x is equal to -1. No, don't do -1. Do -7. Because -7 minus 1 would be a -8, and the y would be equal to -2. So let's start plugging these in. So we have 0, -1. We have 1, 0. We have 9, 2. So 9, 2. -7, -2. 1, 2, 3, 4, 5, 6, 7, 2. So 43. So this is one of the interesting ones. So the line is going to kind of look something like that. Right? So for our domain, right, what x values can we go to? And we can go from -infinity to +infinity, right? Our range is our y values, right? And there's nothing stopping this range. So this range can also go from -infinity to +infinity. Our point of inflection, there is the point of inflection would be the center of the curve. Wait, did I draw this wrong? No, I didn't. Okay. So we're looking for like whatever is going to be like the center value of the S-curve. So if you can imagine this curve would, I'll drag it over. If we didn't have the -1 under the root sign, it would actually be right here. This is what the curve would look like, right? And the middle of that curve is at 0, 0, but because we shifted right 1, it looks like that. So the point of inflection is going to be where like the middle of the curve is going to be. So that's going to be this here, right? That's exactly where it's going to be at. So that's at 1, 0. So now as x goes to -infinity, right, y is going to go to -infinity as well. You see, if we go that way, it's going down. Now as x goes to a positive infinity, so we're going this way now, y is going to keep going up. So it's going to positive infinity. It's increasing. So this is where the point of inflection is important. So our increasing interval is going to be from, remember, we're looking at the x values here, is going to be at that x value 1. Oh, sorry. Wait, I lied. We are, if you look at the curve, we're actually increasing from forever. We're going basically like that. If you kind of just like think about it in that aspect, there's just a little kind of in there. So if you look at the whole curve, we are actually increasing from -infinity to positive infinity, and we're decreasing never. Yay! Sorry, hold up, let me pull up my phone. Okay, this next one is another cube root one, and we can look at it and let's just always try to think of our transformation so we can kind of understand what's happening to the graph here, right? So we have a 1/2 shrink of the whole graph, and then we are moving the graph horizontally, so we're moving it to the left 3, and then we're moving it down 5. So let's start by just putting some points down. Let's see. X is going to equal, well, let's see. So remember, it's cube root, so our easy ones are 0, 1, and 8. So let's try to get those values. So if we plugged in, let's see, -3, y is going to equal 0 times 1/2, which is 0 minus 5. So, and then let's try to get 1. What do we have to plug in to get 1? We could plug in a -2. That's going to give us a -1. And then -1 times 1/2, the cube root of 1, -1 is -1. -1 times 1/2 is 1/2, minus 5 is equal to 4 1/2, which is equal to, yeah, let's do 4 1/2. Now, x, let's think about 8. We could plug in x is equal to 5. That would give us 8, which means that the cube root of 8 is 2 times 1/2 is 1 minus 5 is -4. I don't really think, let's think of other easy ones. X is equal to, let's do one more. Let's do negative, what would be -11? No. -10, no, sorry. Yeah, -11. Sorry, I had to think about it for a second. So -11 is going to give us -8. Cube root of -8 would be -2 times 1/2 is -1, minus 1 is -6. So this is a good amount of points here. So we can do -11. Oh, I guess we don't really have that on the page. Oh, it's kind of aids. We'll put it down here just for the love of it. 1, 2, 3, 4, 5, 6. I would try to find a different one on your exam. I wouldn't go off the page, but I'm going to go off the page for the sake of just showing you how this works. 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, and then just 4.5. I think that should be a negative 4.5. Yeah, that's a negative 4.5. So we got 1, 2, 1, 2, 3, 4 into half. So we got a little dot in the middle there. And then we have 5, negative 4, 1, 2, 3, 4, 5, 1, 2, 3, 4. Oop, see, it almost looks just like that, very similar to that curve that we had above it, right? Except it's a little shrunk because we have that 1/2 shrink. It's not as drastic of a curve, and then it's shifted. Remember, over and down. So if we look at our domain is going to be again from negative infinity to positive infinity. There's nowhere where we have problems. Range is also going to be from negative infinity to positive infinity. Our point of inflection is where it's going to be flipped at. So let's see. The inside. Okay, so our point of inflection actually comes from the inside x value here. So we have x plus 3. We want to figure out where that is equal to 0 at, right? So x is going to equal 0 at negative 3. So if we plug in negative 3, which we already did, we get negative 5. So we found our inflection point is actually negative 3, negative 5, which is one of those points that we put down. Now our end behavior is x goes to a positive infinity, right? If it's going this way, what's happening to y? Y is going up. So y is also going to a positive infinity, and then vice versa. As x goes to there, y goes down. So negative infinity, negative infinity. Now we're increasing once again always. So from negative infinity to positive infinity, and none for decreasing. Now let's move on to 45. Okay. The formula for the distance a submarine lookout can see is d is equal to the square root of 1.5h, where d is the distance in miles and h is the height of the lookout above the water in feet. How high will the periscope have to go to see an island that is 4.3 miles away? So we know that 4.3 miles away, right, is our d value. It tells us that distance a submarine can look out is d. So we can set, and then we're looking for the h value, right? How high? So we're solving for h. So we really have 4.3, our d value, is equal to the square root of 1.5h. Now all we have to do is solve this. So remember we can, so let me get a little smaller thing here. So what we're going to do is we're going to end up squaring both sides, right? Because when you have a root squared, it brings it out. So we have I don't like that. Let's fix that. So now we're going to have 4.3 squared is equal to 1.5h. And now we know that h, right? Because if we divide both sides by 1.5 by 1.5, h is actually equal to 4.3 squared over 1.5. So now we can move on to formula 46. The formula for the distance required of a moving object to reach a specific velocity is v, where v is the velocity of an object, a is the acceleration of the object, and s is the distance required. What distance is required for a car to reach? Okay, so we're solving for distance, which is our s value, right? That's what we're looking for. So we're given that velocity is 72 kilometers per hour. So let's do, and acceleration is 10 kilometers per square second. So we know our v value, right, is 72 is our v value. And then we know 10 is our a value. So now all we have to do is plug this into the equation that we're given. So we do 72 is equal to the square root of 2 times our a value, which is 10, times s. So we're solving for that s value, so let me move this over and up a little bit out of the way here. So we can do, remember we square both sides to get rid of that root. So we have 72 squared is equal to 2 times 10 s. So we know that 2 times 10 is 20, right? So we can really just divide this side by 20, divide this side by 20, and we know that s, our distance, is equal to 72 squared over 20. The formula for the speed of light, for the speed of a falling object is this, where v is the speed and d is the distance. Solve for d in terms of v. So we're looking for d and we're solving it in terms of v. So we're not actually giving a value here. We're just moving variables around. So this is arguably a little bit easier because this is what we've already been working with. So we're solving for d. So we want everything else to be equal to d. So currently we're given that v is equal to the square root of 64d. So how do we isolate this? We square v, right? So we do v squared is equal to 64d, right? Because if we go back, we square both sides. It's the same thing. So now we have v squared is equal to 64d. And now we're solving for d. So we're going to divide each side by 64. And we have d is equal to v squared over 64. Now for the last one. The equation for the period of a pendulum is t equals that. T is the time in seconds, L is the length in feet. Find the length of a pendulum with a period of 3.4. So we know the period t, right? Because period is t. So we have 3.4 seconds is equal to t. And we're solving for L. L is the question mark, right? There we go. That's a really terrible question mark. Let's try that again. So we can do 3.4 is equal to 2 pi square root of L over 32. Now this might look intimidating, but it's really not that much. So we can do 3.4, or let's start by doing this real quick. First thing we want to do is divide both sides by 2 pi, right? Because we want to move everything over that isn't L. So now we're going to have 3.4 over 2 pi is equal to the square root of L over 32. Now we're going to square both sides to get rid of that root, that ugly root. And we're going to have 3.4 over 2 pi. All of this is squared, not just the top part. Let me move this over because we're running out of space. Is equal to L over 30. Oops, that's not, no, that's a 4. L over 32. And then how do we get rid of stuff in the denominator? We multiply both sides by it. So we're going to multiply by 32 and multiply by, not there, multiply by 32. So our final answer for this one, and I apologize for running out of space here, so I'm going to just try to kind of move all this out of the way here. I know it's going to kind of make it a little muddy, right? Is going to be 3.4 over 2 pi all squared times 32 is equal to L. Thank you for tuning in, Twin. I hope this was able to be helpful. If you have any questions, holla at your boy. Take care, boy.